Imagine a mathematical transformation, like a rotation or reflection, that manipulates space without stretching, shrinking, or distorting any angles. We call this kind of transformation a unitary operator. Formally, it is an isomorphism of an inner product space onto itself. Look at the equation on screen. Applying our operator t to vectors x and y yields the exact same inner product as the original vectors x and y. Because the inner product dictates both the lengths of these vectors and the angles between them, keeping that inner product constant guarantees the geometry of the entire space remains perfectly intact. Let's look at the algebra driving this rule. By shifting the operator t from the left side of the inner product to the right, it transforms into its adjoint, t star. We are left with the inner product of x and t star t y. For this new expression to equal the original inner product of x and y for every possible vector, the combined operation t star t must do absolutely nothing. It has to be the identity operator, I. Since t star times t equals the identity, the inverse of operator t equals its adjoint. This gives us a massive computational shortcut. Finding the inverse of a complex transformation usually requires heavy, tedious calculation, but for unitary operators, you just find the adjoint. Hoffman and Kunze's theorem 13 translates this to matrices. An operator is unitary if and only if its matrix representation in an orthonormal basis is a unitary matrix. That means A star times A equals the identity. There is a slight terminology difference depending on the numbers you use. If your matrix consists entirely of real numbers, the conjugate transpose becomes just a standard transpose. In that specific case, we call it an orthogonal matrix. Notice the formulas listed below the matrices. These matrices perfectly preserve the norm, or length, of any vector. And if two vectors start out orthogonal to each other, multiplying them by matrix A ensures they stay orthogonal. These matrices behave this way because their column vectors form an orthonormal basis. The preservation of space is structurally hardwired into the matrix itself. Let's apply this to a specific example from page 305, the 2x2 real rotation matrix. If we set up the multiplication of this matrix by its transpose, the cross multiplication produces expressions with sine squared plus cosine squared. By trigonometric identity, those terms reduce to 1, leaving zeros on the off diagonals. It yields the identity matrix. Now, let's test this. Here is a general complex 2x2 matrix. Pause the video, compute A star times A, and find the equations needed for it to equal the identity matrix. Here is the expanded multiplication. Setting the result equal to the identity matrix generates specific constraint equations, like the absolute value of alpha squared plus gamma squared equals 1. These algebraic constraint equations are the mathematical mechanisms that force the rows and columns to act as independent orthonormal sets. Because all unitary operators are invertible, you can multiply multiple unitary matrices together. The resulting matrix, C, will always be another unitary matrix. Mathematically, they form a group. You can sequence these geometric transformations infinitely without ever breaking or distorting the structure of the space. To recap, unitary operators preserve geometry. In operator form, t star times t equals I. In matrix form, A star times A equals I. These equations give us the exact conditions to model systems conserving probability and energy, making them bedrock tools for quantum physics and advanced spatial geometry. If this breakdown helped you grasp unitary operators, like and subscribe for more linear algebra deep dives directly from the Hoffman and Kunze textbook.